eigenfunctions of the original Hamiltonian. Okay. So we're going to need a better notation here. Right? So let me associate this particular. So this one we said that H not phi naught. This was we said that the zeroth order wave function was the eigenfunction of the arbitrary Hamiltonian. So let me say that this is E naught. Let me associate this particular eigenvalue by the index m. Okay. Right. And now I can then the eigenfunctions of the original Hamiltonian are going to form a complete basis. Okay, so that's the phi I. They are complete. Okay, and each of them has eigenvalue ei. Okay, so now I'm just I will expand this phi 1 onto this basis. Okay.
What's on the top right of phi m?
Zeros.
Oh.
Right. So you can, let me say that, maybe to be more clear, okay, I'm going to set the problem here, the zeroth order energy value will be equal to the m's eigenvalue of the original Hamiltonian. Okay? So, a summation over all of the eigenvalues. And then this is an expansion, and let's use something we didn't use before. Okay, let's use an. And to indicate that we're calculating the first order correction to the wave function, let's say that this is an1. Something like this. Right? So now I go ahead and plug it into that equation. So this equation over here. So what do I need? Okay. So the strategy is still you plug in that expression and then you test it with some other basis. Okay. And then reading directly you get and phi of 0 we will just interpret it as phi m. Okay. So this is just this equation written in the expression. Now let's choose some arbitrary eigenstate of the original Hamiltonian and test this equation. Okay. So what's going to happen is, you see, if I test this because of this orthogonality, I'm going to eliminate this term. Right. Okay. So I'll go ahead and test this with phi I. Correct? So now we ask, what is this? Okay. Again, you interpret this as you operate on a bra from the right. Okay. So this gives you EI. Okay. So Okay. So now since these are all numbers, right, I can take this graph across to here, right, and I'll get a delta and I. And then over here we have delta and y. So for the case, let's write the whole thing out. That means did I use 0? N equals 5%. And of course, this is going to single out the ith component from the summation. Right? So we get that AI to the first order, and this is equal to minus 5i. So now let's consider the case that I is not equal to m. Okay, trivially we can just set this to 0 then. And we get that for I not equal to m, we have em minus I over 5i. So the first order correction, although the first order correction to the eigenvalue, to the eigenenergy, is only dependent on the diagonal elements of the perturbation. The first order corrections to the eigenfunctions are dependent on the off-diagonal elements. So, the wave function changes more than eigenvalue. That is the basic idea. So now, going from this step to this step, you can already see the problem you're going to have if you have degeneracy, right? Now, what if EM and EI are the same? Then this procedure is not valid. Okay, let me just talk for 5 more minutes and we'll be off. So what happens if M and I are equal? Okay, if M and I are equal, then this would turn into, okay, so for I equals to M. The right-hand side is 5. The right-hand side is 5i, which is m now. And this is just, we can compute this. This is just the first order perturbation, right? And then so this minus this plus this. The right-hand side is 0. So you cannot solve for this. This is not determined. Okay? But there is also still a way to determine this, and that is we want to fix the length of the wave function. Okay, and we can do that by requiring that. Let's have phi m and the real eigenfunction. Let's require that this be equal to 1. Okay. So this fixes the norm of this function here. It doesn't normalize it, certainly. And when you do perturbation theory like this, after you solve for the correction in the wave function, because you're not computing the entire wave function, so in general that is not going to be normalized. If you compute the entire wave function, if you keep on expanding, okay, then it will be normalized. But that will not be normalized. And at the end, after you're satisfied with your result, you need to renormalize your wave function. But over here we fix this, and this is a convenient choice because if I know this is 1, okay, what does that mean? Then the first order correction phi 1. Okay, yeah, the first order correction phi 1. This will be orthogonal to the original eigen function, right? Okay, and this is what we just said here. So to solve this problem of indeterminacy, we can just fix the length of the Eigen function to be 1 when it's projected onto this component. Okay. So next time we're going to talk about second order perturbation theory in the energy. And really, you don't get much by computing the wave function correction to second order, because the algebra gets messy. And then we're going to talk about the time value model. Finish chapter 6. Okay. Are there any questions before you go?
Is the homework too hard or too easy?
That's right.
Just right.
I feel they don't feel it's too easy.